Hello, you are welcome once again to Dr. OJ Digital's tutorial class. This is another question coming from polynomial approximation of Taylor series. But this time around, we are going to use Hessian matrix for the approximation. Now, let's get started. Solution. Let's recall, for second order approximation of the Taylor polynomial, we have this formula. T2 x comma y is equals to f of x comma y plus the gradients of f of s comma y, but at the point given, let's say the point given, let's write it out, x comma y as well, the transpose of that gradient with respect to x comma y, then plus half of s comma y, then the Hessian matrix of s comma y. So here we could write, we could replace this by 0 if we are given, if the intervals or the pointer origin, we put 0 comma 0 here. Whatever we are given as the origin. Oh, this question is not complete. About or around 1 comma 0. Sorry. So because in this case now we are given what? We are given the neighborhood of our approximation is 1 comma 0. So we are going to use 1 comma 0. But if you are given the origin, origin will be 0 comma 0. So this time around now, we are going to change this to what? 1 comma 0. Okay? Yes, that is that about that. All right. Now let's get started. Let's get started. In the course of our explanation, we are going to see the meaning of the Hessian. Let me write the Hessian matrix formula. Hessian. Hessian of 1 comma 0. Let me write it out. This is Hessian. Fxx of 1 comma 0. I think okay. Fxy, that is the partial derivative of x, f with respect to x and y, 1 comma 0. Then fyx 1 comma 0. Then fyy 1 comma 0. Okay, so that is the Hessian matrix at 1 comma 0. All right. Now, having known this, we have to take this one by one. Don't forget, this is T, transpose of this. Okay? Now, what do we do here now? Okay. We just have to start with this particular first term. Now, how do we go about this first term? Fine. We know already that our f of x is x exponential y plus 1. So from here now, f of 1 comma 0 will be when x is equals to 1, where x comes first, and y is equals to 0. So if x equals to 1, you have 1 times exponential 0. That is 1 times 1. That gives us 1. Because anything raised by 0 is 1. That is the value of this. Then plus 1 here. Plus 1. Let's finish it up. So 1 times 1 plus 1. Okay. That will be 1 plus 1. And that is 2. Okay. I hope that is clear. So this is 1 times 1 plus 1 here. That's 2. So we have gotten the value of f of 1 comma 0 as 2. Fine. Now, this particular, this is we will call it nabla. Nabla. This symbol is called nabla. And it simply means the gradient of this function, the gradient of f. So now, let's look at how we are going to deal with that. Let's look at how we are going to deal with that. Okay. Now, this gradient of f at around 1 comma 0 simply means that you're going to have this f of x fx rather at 1 comma 0, that is f success x, f success y at 1 comma 0. Okay, that is it. It's going to be column vector. All right, column vector now. But because we put t there, we are going to transpose it. It means that, which means the gradient of f around 1 comma 0 with transpose t now will become what? Will become this fx 1 comma 0, no, sorry, and the fy 1 comma 0. Yes, you transpose it. When you transpose a column vector, it becomes a row vector. I hope that is understood. Okay, let's now find the value. Our function, the problem given to us. I think I've cleared the problem. The problem is okay. F of s comma y, I think is equal to x exponential y plus 1. Okay, I think that's the problem. Okay, now let's deal with that. So we want to find the gradient, and to find the gradient we have to find the partial derivative of f with respect to x. So f x at 1 comma 0. Okay, let's do it in such a way that you understand it very well. Don't let us rush. Fx, fine. Here, if you differentiate x here, you know x is multiplying exponential y. I hope you are getting that. Okay? Now if you differentiate x here, you get exponential y left. Because when you differentiate x, it is 1. So you multiply it by exponential exponential y. And this one is 1, it's not x, so it will be 0. So fx is exponential y. Beautiful. Which implies fx at the point around the neighborhood of 1 comma 0 will be, that is when x is 1 and y is 0. And what we have here is what? Y. So that will be exponential 0, which is 1. Okay? Hope that is clear. Now we have done that. Now fy. Okay? Fy, we go back to the function. You differentiate with respect to what? Y, partially. You know, you see, if this is one is we can use product rule here. If you differentiate x, ordinarily you are not supposed to differentiate x because it will give you 0. X is not what we want to differentiate with respect to. So we differentiate y. Okay. Now, if you differentiate y, you are going to have 1. Use that 1 to multiply this x. You have x, then repeat exponential y. This will be 0 because it's not y. Okay. So that implies f, the partial derivative of f with respect to y around the neighborhood of 1 and 0 will be, that is when x is 1, this will be 1 times, and y is 0, exponential 0. Okay, that is what? 1 times 1. It's also 1. Good. It's also 1. I hope you are following. Okay, you are following. That's very good. So we are done with this now. That implies what? That implies the gradient around 1 comma 0 is now what? Is now 1 1. So but if we transpose it, when you transpose it now, and transpose it, you have what? It will be 1 1. It will be row vector. So we are actually done with that too. Okay, now we need to, from our formula, I think I've cleaned the formula, then at least we should be able to remember it all fine. Now we actually have to deal with our Hessian matrix as well. So our Hessian matrix now, H of 1 comma 0, we said it is fxx, that is second. Hessian matrix is used in second order derivatives. Okay, 1 comma 0, you can see that we use gradient for only first order. That's why you have x, y. But now when it becomes 2, use Hessian. Okay, we have f of xy 1 comma 0. Then we have f of yx 1 comma 0. I think I'm just writing this for more clarification. Y 1 comma 0. So let's quickly do that now. Now to do that, we have to find the partial derivative of all of them. So I think let's start with fxx. fxx, where do we have fx? Our fx is what? Is exponential y. Now if you want to differentiate this with respect to what x again, because we said fxx. So if you want to differentiate with respect to x, and unfortunately you have exponential y. Fx is partial derivative of f with respect to x is exponential y. You now want to differentiate it with respect to x again, and unfortunately you don't have x, so this will be 0. This value does not have x, it will be 0. Okay, now the next one, fxy. Let's now fxy means after you have differentiated your fx, now differentiate it with respect to y again. And you know fx is exponential y. So if you want to differentiate it with respect to y now, you know, when you differentiate the exponent rather, it's going to give us 1. Multiply the whole thing here by 1. Now I have 1 times exponential y. Note something. Note, okay, fxy is same thing as fyx. Yes, they are the same thing. If you try it, you'll get something there. Fxy, if you differentiate fyx, I'm saying fxy is same thing as fyx. Should we check that? Do you want us to check it? All right. If you want us to check it, all right. Now look at this now. This is fy. If you want to differentiate this one with respect to x back, when you differentiate x here, it is 1. So 1 times everything you have here is exponential y. Now see? So fxy and the same thing as fyx. Okay? Partial derivative of xy is same thing as partial derivative of fyx. Now, this one implies that if we now say fxy with the neighborhood of 1 and 0, okay, I hope we are seeing what I'm writing. Good. Now, x is 1, y is 0. Unfortunately, there's no x. So pick x. I mean, we pick y that is 0. So that will be exponential 0, which is what? Which is 1. Which is 1. Okay, I think we need to be writing this thing somewhere so that we don't forget. All right, let's go ahead. Now we have actually done that too. So it remains the last one, fyy. It remains the last one, fyy. Let's go to fy. Our fy is this. Now to differentiate it with respect to y again, that means we differentiate the exponent here. It's going to give us 1. 1 multiplying x. You have x exponential y. Okay, because if you differentiate x, it will be 0. 0 times this. If you use product rule, saying after you have differentiated this, multiply by this, plus differentiating this, multiply by this, you are just wasting your time. Because if you differentiate x, it will be 0. 0 times everything here is 0. So you have to differentiate that y that you need. Okay, this implies fyy with respect to 1, 0, that is around those points, will be what? 1, because our x is 1, times exponential 0. That is 1 times 1, which is 1. Okay, I think that we are following. Beautiful. So now let us write out. Let's write out our Hessian matrix now. Hessian matrix. Hessian matrix now. H around 1, 0 will now be fxx 1, 0, fxx 0, fxy, we got 1. Then fyx is same thing as fx, I think 1. And this is also 1. Good. 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 Okay. Now, let's make use of some substitution so that it will be easier to solve this problem. Let's make use of some substitution so that it will be easier to solve the problem. How? Fine. I want to introduce h and k. Now say let hk This point are extensions of this one. This one, H, is an extension of point X on the axis, on the x-axis, while K is an extension of point Y on the y-axis. So let's call this one. Remember, we said the neighborhood of our points are 1 and 0. So now, if this one is an extension, increment in X, that means H will be X minus 1. And this we want to change our X, Y with respect to H and K. So subtract this value given from X. We assume that this value is X naught now, and which one is Y naught. So subtract it. So X minus 1, comma, K will now be Y minus 0, which is X minus 1, Y. Okay? Now you see how we are going to make use of that now later. So now the second degree that we are looking for, T2 of S comma Y, that's the second degree, is equals to F of 1 comma 0 plus, the gradients. And what do you get for our gradients? I think we get 1, 1. Yes, I think that's what gets X, Y. But this time around now, everything will change to HK. HK, yes. Then plus half HK, H of HK. Beautiful. Beautiful. I've shortened my Hessian as H. Alright. So let's fix it up. Our F of 1 comma 0, what did I think we got 2. We got 2. Then plus. Now let's multiply out. We want to multiply this matrix by this. 1 times H, that's H, plus 1 times K, that's K. I hope you got what I did there. 1 times H plus 1 times K. Beautiful. Then plus half of now HK. Okay. Now our Hessian matrix is what? Hessian matrix 1, 0, 1, 1. HK. Oh yeah, we are going to find out this before multiply by this. So we have 2 plus H plus K plus now half of HK. Okay, it's a matrix. Then let's take this. 0 times H. 0 plus 1 times K. K. That settles that. Okay. Now 1 times H. That's H plus 1 times K. That's K. I hope you can still remember how to multiply in matrices. Again, 0 times H, that's 0, plus 1 times K, that's K. 1 times H, that's H, plus 1 times K, that's K. Okay, let me write it on. Let me write it on the upper part of the board so that we see it clearly. All right. So we are now having what? T2 of S comma Y. I hope you can see what I'm writing. All right. Is equal to 2, all right, plus H plus K, all right, plus half HK. Now, with this now I have K, H plus K. It's a matrix. It's a matrix. Okay. So, now we have to have 2 plus H plus K plus half. Now, let's expand this now. H times K. So, we have HK. There is H times K. HK plus K times this. That's K into H plus K. Yes. Again, H times, this one is 2. This, what type of matrix is this? This one is what? 1 by 2. The row is 1, the columns are 2. Then we are multiplying by, what type of matrix is this? 2 by 1. So when you multiply the 2 here will swallow the 2. So it remains 1 by 1 matrix. That's why we are having only one row. That is it. Okay. So we are almost done. We are almost done. We are almost done. It's very simple. Very, very simple. Don't panic. Take your time. You understand it. Now let's expand. We have 2 plus h plus k plus half of hk plus hk plus k squared. Yes. So this is what? 2 plus h plus k plus half of 2hk plus k squared. Okay, that will be what? 2 plus h plus k. I want to explain everything thoroughly. So multiply this by half plus hk, because 2 will cancel 2 here, plus k squared all over 2. I hope we are following. Good. Now let's try to let's try to finalize the result here. Let's try to finalize the result. Don't forget, recall, h is what? X minus 1, and k is y, because y minus 0 is y. So let's fix it up. Oh yeah, let's fix it up. I want to fix this up now. Fix it up. Yeah. T2 of x comma y, that is the second, this T2 means second order degree that we are looking for. 2 plus h is what? X minus 1. Okay, plus k. Plus k is y. Then plus h again, x minus 1 multiplied by k is y. Then plus k, y squared all over 2. Yes. So this one will be 2 plus x minus 1, all right, plus y plus x minus 1. I hope we are following. Okay. Oh, sorry, we have to multiply. Sorry. X times y is xy, then minus y. Sorry about that. Then plus y squared over 2. Okay. So the answer will come out now. Very simple. So look for the common factors. Like terms, this will cancel this out. Yes. 2 minus 1, that will be 1, plus x plus xy plus y squared all over 2. So this is the answer. That is, the second order degree of this approximation is equal to 1 plus x plus xy plus y squared all over 2. So if you enjoyed this video, if you like it, please like, give it a thumb up, share, and make comments. God bless you. Bye.